Welcome to the IT Free Training video on recursive and iterative DNS queries. When a request is made to a DNS server to resolve a name, it is done using one of these query types. By the end of this video, you will understand the difference between the two and why two types of queries are required in DNS in order to help with scalability and availability. In this example, if a desktop computer attempts to resolve a DNS name, it will first check its local cache to see if it has been resolved previously. If the DNS name is not in the cache, the desktop computer will contact its locally configured DNS server or servers in order to try to have the DNS name resolved. In order to resolve the request, the desktop will send what is called a recursive query to the DNS server. A desktop will normally have two DNS servers configured for redundancy. More can be configured. However, if you have a large number of DNS servers configured locally, this can slow down resolution time. This is because each time a DNS name cannot be resolved, each DNS server needs to be contacted before the computer will report that the DNS request could not be resolved. A DNS server that is configured to respond to recursive queries takes responsibility for the request and will attempt to contact other DNS servers if it cannot answer the DNS request itself. That is, if it is not holding the answer to the query in a zone file or in its cache. The first step in this process is to contact a root hint server, assuming this information does not already exist in the cache of the DNS server. You can see that caching is used in every step of the DNS process in order to reduce the number of DNS queries that need to be resolved. This request is different from the first request in that it is an iterative query. An iterative query works like this. If the DNS server does not know the answer, but has information that may help resolve the query, it will respond back with this information. In this case, the root hints server does not know how to resolve the address itfreetraining.com, but what it does know is the address of a .com DNS server that may be able to help find the answer. If the DNS server attempts to send a recursive query to a root hint server, this request would be rejected. Since a root hints server forms the top of the hierarchy of DNS, it is important they are always available. For this reason, they cannot afford to get overloaded resolving DNS requests, and thus you can see why two types of DNS queries are required. If the root hints servers were configured to resolve recursive DNS requests, you could imagine how many requests the DNS servers could potentially receive, as everyone on the internet could use the root hints server to resolve DNS names. Because of this system of recursion, iterative queries, and DNS server caching, the root hints server only receives a small percentage of the overall DNS traffic on the internet, ensuring that they are always available. Now that the DNS server has the addresses of the .com servers, it will send a second iterative query to the .com servers asking if they know how to resolve itfreetraining.com. These DNS servers will also not know how to resolve itfreetraining.com. However, they will return the addresses of the authority DNS servers for itfreetraining.com. Using this information, the DNS server can send a third and final iterative query to the itfreetraining DNS server and obtain the IP address for itfreetraining.com. You can see that the whole process took 4 queries. One recursive query to the desktop's DNS server, a second one to the root hints server, a third to a .com server, and fourth to the itfreetraining authority DNS server. This may seem like a lot of queries for one address, but once the initial work is done, the results are stored in cache for each step. So, if the client was now to ask for the IP address of google.com from its local DNS server, the .com servers would already be stored in the cache. The DNS server does not need to contact a root hints server a second time, and this time will contact the .com server to obtain the address of the authority servers for google.com. When DNS servers are deployed on a network, some companies will choose to switch off recursion on certain DNS servers. For example, if a DNS server is on a protected secured network. A DNS server in this case should never be contacting the Internet directly. For this reason, recursion is disabled for additional security. Another common example is if a DNS server is holding authority zones. The companies want to maximize the responsiveness for answers from the DNS server for those authority zones. For this reason, recursion is switched off. This means the recursion queries will go to DNS servers that are dedicated for that particular purpose. For example, all ISPs should have DNS servers that are dedicated to resolving DNS queries. To sum up what was covered in this video, recursion is when the DNS servers take responsibility for name resolution. This means that if required, a DNS server will contact other DNS servers in order to find out the answer. In contrast, iterative querying is when the DNS server responds to the request with the best information it has, either from its zone files or its cache. If it does not know the answer, it will respond back with any DNS servers that it knows of that may be able to help answer the query. If the DNS server does not know the answer and does not know of any other DNS servers that can help, it will respond saying the DNS query cannot be resolved. It does not attempt to contact other DNS servers in order to obtain the result. That covers it for recursive and iterative queries. By using the two together, this allows DNS to have a hierarchical nature while ensuring that DNS servers holding the answers are not overloaded and thus helps with reliability and scalability. Thanks for watching this video from IT Free Training. This video is only one of the free videos available in the DNS course. Other courses are available for free on our web pages or YouTube channel. Thanks for watching, and see you next time.